So if you have questions about the assignment 2, probably the best thing to do is talk to me after class. Just a reminder for the activation functions that our goal is to find an activation function that first off has the right range. Okay, is probably the most important one in our final activation function. And you don't have to have an activation function at all. You know, in this sense, identity would be fine for the output. Why would you not want the identity function for all of your activation functions in your entire network? Yeah, it'd end up being a linear combination. So what you could express would be very, very little, wouldn't be very expressive. So here's what we're going to talk about today. We're going to finish off regularization. We're going to talk about batch normalization, and then we're going to get into various gradient descent algorithms. So we talked about a bunch last week, and the three we didn't talk about are parameter sharing, dropout, and ensembling. And the idea of this regularization is basically we create a network that generalizes better. So for parameter sharing, well, if we share parameters, there are fewer parameters. And therefore, it's not as, we don't have as many degrees of freedom. Give me an example. Convolution. So in a convolution, we are sharing weights. I guess the way I would describe it is across the area of the input. And it would certainly be possible to create models where we didn't have that. If we just had fully connected layers, right, then we would be allowing basically different weights for the pixels in the bottom right as opposed to the top left. Why do we like the parameter sharing for convolutions? Besides just the fact that it regularizes, yeah?
Usually we're looking for some kind of like feature in our data, and if the feature is in the top left or the bottom, we don't really care.
Yeah, if you're looking for an eye, you want to find an eye wherever you find an eye. And it's much easier to train a single convolution, single filter, to learn what an eye looks like than it is to try and train all of the weights dealing with all of the different little areas, independently learning what an eye is. That's really it for parameter sharing, right? That's just yet another way. Ensembling. So ensembling, a fancy term for basically using multiple models. We've almost seen something like this. I think we saw a case in the first week when we were looking at dog-cat where we did data augmentation at test time, at inference time, and we went ahead and did four different augmentations plus the original, and then just voted or averaged, I think averaged maybe what the result is, and got a better result. We can do the same sort of thing with just different models. If we've got model A, model B, model C, we train them separately, and then we'll probably generalize better if we use the best of 3 or average result rather than just one.
Is data augmentation a regularization technique?
Data augmentation it's a regularization techniques, right? I guess it can be called a regularization technique. It certainly would lead to better generalization, just like adding more data. So it's your poor man's alternative to adding more data, right, at training time. Where would we come up with multiple models? Give me some potentials. Evan, yeah? Other machine learning techniques. Yeah, you could use random forests, for example. That's one possibility. What if we stay within the neural network realm? I mean, we could have different architectures. VGG and Inception and ResNet, right? Use those all. What if we don't want to go to the bother of creating different architectures? What about just the same architecture and just try it 3 different times? Would we get different results? Training a model? Why? What would cause it to be different? Different what? What's the randomness that we have when we're training our model? Say that again?
If you're feeding it data in a specific batch or like order.
Yeah, so the selection of the mini batches is randomized. So that's one way in which we're going to end up with different models. And what's another way? Yeah, the initial weights and biases. Okay? Plus, we'll see there are some other cases where during training you may have some randomness. And so we're going to get different results. Okay. How to combine is certainly a question. You could just take the average. You could take the best of 3. You know, if you're looking at probabilities, just take the highest probability, let's say, or the average. You could even view it as how to combine different ensembles is an optimization problem. There are techniques, not used really that much in neural networks, but in general machine learning, of things called like boosting, where you take a model and then you say, okay, I'm going to make a new model whose job is to do well on the things this model does poorly on. Okay? And we're going to weight things appropriately such that this model, for the vast majority, is used. And for cases where it's sort of not doing so good, we weight this model. And we can just keep going with this differencing. So that's an idea of boosting. But we're not going to deal with that too much. So we can. The problem with why we don't like doing this too much is to train in models takes n time. Okay? So it'd be really nice if we could somehow come up with multiple models along the way for free. Okay? And so for free might be stochastic gradient descent with restart. You remember, we look at this and we have a learning rate schedule that looks something like this, where we reduce the learning rate and then we increase it again. And then we reduce the learning rate and then we increase it again. And then maybe we reduce it even slower. Okay? When we're training a model, actually, every time we run backpropagation, we've got an updated model, right? So we've got an old model, and we've got a new model. And in fact, if we're running, I don't know, let's say 10 epochs, and each epoch has 10,000 mini batches, how many different models have we created along the way? 10 epochs, 10,000, yeah, it's 100,000 different models. So those are all potential candidates for our ensemble. Now, is the very first model a very good candidate? What's our first model have for our weights? Random, so not a good choice, right? Even if you do a bunch of different random ones, it's not going to be very useful. So if we look at our learning that happened over time, where might be a good place to, let me mark our final model. So here's our final model. But we have some other potential models along the way, right? This one was pretty good, right? It had gotten to a reasonably low loss. This one would be pretty good. By the way, what are our dimensions here? Our axes? Time and learning rate. I just want to make sure we're not looking at the loss here, right? This is the learning rate. We assume as our learning rate, as we're going over time, that our loss is going down. Although we probably are increasing our loss when we jump our learning rate back up. So what we could do is we could just say, well, when we're doing stochastic gradient descent with restarts, before we restart, save the model, right? We can code that in. And so however many restarts we have, we'll have that many models. Yes, our last model will probably be better than the previous models, but there'll be the differences in the work. Question makes sense? Or that idea makes sense for the ensembling? Okay, and just in general for ensembling, if you look at, for instance, the you guys familiar with the Netflix prize? So it was quite a while ago, but the Netflix prize was Netflix came out with a bunch of ratings of users and movies. So there were, thousands of movies and tens of thousands of users, and we had this sparse matrix where, most users have only rated several movies. And your idea was for a given cell that didn't have a value in there, you were trying to predict a value. And they held back data for this. So and they gave out $1 million prize, I think, if you could come up with a accuracy that was 10% better than what they had. Okay? And so this was the first real prize for machine learning that I'm aware of. And that was in the late 2000s, I think, as I remember. So what happened was there were a bunch of people who were kind of doing well at this. And what they would do is form into groups. So they would cluster together and basically do ensembles. I have a good model, you have a completely different model, but it's good too, and you have a model, let's combine together. Okay? That's what often wins Kaggle competitions too, is if you look at the Kaggle, it says you can only join teams together up until a certain amount of time. That's what they're talking about, is folks on the leaderboard will get together and say, hey, let's work together. Okay? Either sharing ideas or just saying, let's just take our models and ensemble them. All right. Dropout. So dropout is this form of regularization. We specify a dropout probability. You have to be careful here because depending on the API, sometimes it's the probability of keeping a given weight, and sometimes it's the probability of dropping it. So you want to know which one it is. Okay? So we specify for a given layer what our dropout is. And what happens is each input with that probability will get set to 0. So if we are at layer L, right, and then we've got 2 inputs coming in, then we have 6 different rolls of the dice, right, to see whether this input goes away or this input. I take it back. We're not actually going to do the weights. We're going to do inputs. There are several different ways that you can do dropout. So one way is to just kill inputs, and another way is to sort of zero out the weights. Killing the inputs is a little simpler, yeah.
So it's not the neurons in the dropout layer for themselves that are like getting zero, it's the inputs to the dropout layer that are getting zero.
That's right. It's the inputs to the dropout layer that are getting 0.
And it's 1 times 0.
It's a 1 times 0 for the mini batch, right? So we got our entire mini batch, and we're going to say, okay, as we're running this particular mini batch, we're going to zero out the input. So it's not going to propagate forward, and it's not going to propagate back either. So
Sorry, this is referring to the A coming from the
exactly. So we're doing is we're zeroing out particular A at L minus 1s. So this allows us to get rid of raw features, right? Our input. So we could do this at layer 1. So this basically says, let's just ignore some of the input. So that's making our input be sort of noisy. And that allows us to force us, the network, to use some of the input that might not otherwise be using. Images is not particularly a good example. Let's say we had structured data, where, again, the house price example. So we have number of bedrooms and square feet and whether it has a pool and all these other things. And maybe the square footage is like a really big determiner. And so the network is not really learning to take into account very well the number of bedrooms. If we kill the square footage. It's going to force it to be learning to do stuff with the other features. And that same thing happens everywhere in the network, right? If we look at some particular neuron in the network, that's learning some particular feature, right? In the case of convolutional neural networks, that might be some high-level feature, like a feather, let's say, you know, or the spines of a feather. And so by forcing the remaining part of the network not to use that, we're making it more robust. We're making it learn, you can think of almost like well, that's probably not a good analogy, but sort of a holographic representation where we're representing it from many different features. And this works surprisingly well. All right. It's important that we're not using dropout at prediction time. Okay? So when you are running the forward pass, normally there's some sort of a flag that says whether you're doing this for training or for prediction or for test. And the dropout layer notices which one it is and sort of turns itself off if it's at prediction time. But there's a particular problem, which is if we look at Z, so we've got a layer that has dropout, what's the magnitude of Z if we do the dropout and we don't do the dropout? Right? So if we have 4 inputs coming in, and we've got a dropout of 0.25, and each of these have, let's say, an expected value of 1, then what's our weighted input going to be? Our expected weighted input using dropout? 3, right? Because we have basically an expected value of 0.75 for each one of those. So we get a total of 3. But when we're doing prediction, what would we expect our weighted input to be? 4. So we need to scale by that factor. When do we do it? We can do it at prediction time, or we can do it at training time. Why training?
It's easier, like why do you want to do it at test time? Like it just feels like more overhead.
Okay, so here's one example. Maybe we're going to, I guess you'd have to look. Over the lifetime of our model, are we going to do more prediction with it, or are we going to do more training? Right? So that's one reason you might want to do less prediction. You might throw your model out there and just be using it over and over and over and over again. Okay? The model that, let's say, determines that you've said, hey, Alexa, you know, or Alexa, or whatever you say. I have a Google Home, so I say, hey, Google. But anyway, the model for that probably got trained a certain amount of time, but is being used for prediction substantially more. The second reason you might want to do this at training time is this would allow you to dynamically change the dropout rate. So you might have a dropout schedule that goes from 0.5 down to 0.1 over time. And so therefore, the scaling factor has got to change over time. You can't really deal with that at prediction time. Okay? So when we're doing the dropout, that is when we are doing the training, we'll scale each non-dropped out input by 1 over 1 minus p. That is, if our dropout was 25%, we'll scale by 4/3 every one of the remaining ones. And this only works in expectation, right? Because it may be we dropped out everything. Questions on this?
So when we're doing dropout, do we necessarily want to make sure that every set of, or at least every neuron and every given layer has been dropped at least once, so like make sure they're not?
Just let randomness deal with it.
But ideally, would we want them to like, because I feel like we're really dropping them out so that the rest can like bear the weight and like focus, extract features separately.
Yes.
So if we did it to all of them, sort of like a K4 cross validation when you like drop one out and then the others deal with it and then you like drop the next one out.
So you could have a more deterministic approach to dropping stuff out, where rather than just throwing the dice, you say, I'm going to drop out one input this mini batch, and another input the next mini batch, and another input the next mini batch. And you could certainly do that. Dropout is just simpler, and you get a nice, you're trying all different possibilities, right? If you've got dropout on multiple layers, then you are independently looking, what happens if I get rid of this input feature and this particular feature in the middle? And so you would have to try and make sure you have all those combinations, and randomness is just the easiest way to do that.
Is there a reason we don't scale the inputs by, say, 1 over 1 minus p hat, where p hat's like the actual portion we ended up dropping out? Just to like keep things more consistent? Like if say we had a 25% chance of dropping out, we ended up dropping out 2 or 4, would we scale our inputs by a factor 2? So
That'd be interesting. We should just go look at the code and see. That is certainly, maybe even a better idea, is roll your dice, figure out how many you're killing, and then scale appropriately so that you're not scaling in expectation, you're scaling in actuality. So yeah, that certainly seems like a reasonable way to go. Yeah. And also that's something you can only be doing at training time, right, rather than test time. There's not a perfect understanding of why dropout works, okay, as well as it does. But one way to think of it is you are creating, for every mini batch, a unique model. Okay? Because it's basically you're taking your original model, and for that mini batch, you're just chopping off particular inputs. And so that is a new model. But all these models share a given set of weights. Right? So it's kind of parameter sharing across all of these. And with automatic combination of these ensembles, right, when you get to prediction time. That makes sense? All right, that's it for dropout. Batch normalization. So batch normalization, let's look at an example. Let's say we have our inputs. Okay, we've got some training we're doing on some inputs. And we've got, a bunch of images. So this is one, and we've got another that's, we've got whiskers, and some other sorts of ones. So let's say it's cats and dogs. Okay? If we did all of our training for cats and dogs on black cats and never any other color cats, and then we went to test time and we had non-black cats, it'd be hard for the model to deal with that, right? Because we're changing the distribution of inputs, what it's seeing. It mostly was seeing RGB all equal the same for cats, and all of a sudden sometimes the RGBs are not equal, and maybe there's different patterns and stuff like that one has to worry about too. So this is called, the official term for this is sort of covariate shift. So we can have covariate shift on the input. And that causes problems. Okay? Similarly, if we have internal to our network, if we've got it at a particular layer, the previous layer is changing its distribution of what's coming in a lot from what it had learned, that's going to cause it to have problems. So ideally, we would have a stability in distribution. Let's just look at one particular statistic, the mean. So let's say we'd like the mean of what's coming in to remain relatively static over time. But that doesn't happen with what we've seen so far in our networks. So if we've got a particular layer here, right, layer L, and we look at its inputs, they're changing all the time, right? Every time we do backpropagation, we're saying, how should the weights here change based on the derivative of our cost function, our loss function with respect to this? But simultaneously, we're saying, oh, by the way, let's also do the same thing for here and here, and all previous layers. So when we make that change, what's going to happen to this input here? Would we expect the mean to stay the same? Not at all. So we have adjusted this value. It sort of would like the mean to all stay. It's being adjusted, assuming everything else stays constant. But it's completely not staying constant. So this is all changing. Our mean is going to change. Our variance is going to change. And therefore, what we do as a result has some difficulty. So in the middle of the network, this is called internal covariate shift. It's a fancy naming for this. Okay. So the idea is, for a given mini batch, it'd be nice if we could make sure that the output from a given layer, let's say this boundary we're looking at from here to here, that the output from here to here had, let's say, a mean of 0 and a standard deviation of 1. In fact, where have we seen this idea of mean of 0, standard deviation 1 before? Normalizing inputs. That's the same kind of idea. We're normalizing not just the inputs, but all the layers. Does the concept make sense? All right. So what are we going to do? We're going to, for a given mini batch, right? And the mean and standard deviation only really makes sense within a given batch that we're dealing with. So within the mini batch, x1 through xm, we're going to take a set of activations from the previous layer, and we're going to normalize them, just as if we were normalizing inputs. So we'll compute the mean and standard deviation of this mini batch. It's an approximation of the true mean and standard deviation, right, across all. But we've got this mini batch. And then we'll rescale. So we're going to calculate mu sub b, that is b for the mini batch, sigma sub b, the standard deviation for the mini batch, and then just rescale all our values. So what layer L will see is a set of activations. Right? It's going to see m different inputs for each of the m original inputs. And across them, their mean and standard deviation is going to be 0 and 1. Does that make sense? All right. So there's a problem with this. Right? There's a good part of this and a bad part of this. The good part about this is that we've got this aspect of the incoming stuff, of our incoming activations that are going to maintain their mean and standard deviation. So they're not going to change all that much. One problem, though, is what happens if we want, so let's say layer L wants, and we can talk about what I mean by wants. So we want ZL to be large. Okay? How does ZL know it wants to be large? Backpropagation, right? We say, what's the derivative of J with respect to Z sub L? We find that it's negative, so we want to make it bigger, right? So Z wants to be bigger. How does Z get to be bigger? What are some ways Z can be big? Weights or the bias, right? So if it just wants the value to go up by a certain amount, then it could just adjust the bias, right? But actually, when it says it wants it to be a certain amount bigger, the bias is going to get bigger, and every one of the weights is going to get bigger, right? And then we're going to tell everyone downstream. Upstream, I guess, is the right, let's see, yeah, the end of the network is downstream. So tell everyone upstream, oh, by the way, we want this to be bigger too, in terms of backpropagation. So Z wants to be large. It's going to adjust its weights, and it's going to tell each of the activations they should be larger too. And so backpropagation is going to be sort of fighting against us because we changed the mean to be 0, and now it's going to say, I would like all these inputs to be larger. And what are we going to do on our next mini batch? We're going to set them back to 0 again. And it's going to say, but I want them to be larger. And it's going to push, so there's this push back and forth. So we do one more thing. So, oh, sorry, one just very slight detail. When we're calculating the standard deviation, right, rather than just taking the sum of squares and the square, we're going to throw in an epsilon here just in case, to prevent any divide by 0. So that's just a small, slight thing that doesn't matter too much. So let me make sure this is also clear. We're calculating this mean and standard deviation and doing the rescaling in a way so that that will be part of our backpropagation. So we're going to actually be backpropagating through our rescaling, okay? Which is where it's going to do this, get this kind of undoing effect, where it's going to undo the rescaling. And there's something I said before that's slightly not true. So if we want to increase the mean or standard deviation of an output, because of how this computation is happening, the gradient's actually going to be 0. So it's not going to push that. Okay? However, what we have done here is reduced our expressive power. Okay? We have reduced the power of our network because the output of a particular layer has a mean of 1, or a mean of 0 and a standard deviation of 1. And there's no way that the backpropagation can change that. Okay? Because every time we're going to go through this batch norm process between layer L minus 1 and layer L, and that's going to force stuff to be 0 and 1, mean and standard deviation. So we're not as powerful because before we could have had from layer L minus 1 to layer L some non-zero mean and some non-1 standard deviation. And so there's less we can express. So it'd be nice if we could get our same expressive power, which is kind of weird because it seems like we're just going back to where we were. But we're going to go back to where we were in a nice way. So what we're going to do is we're going to add a couple more parameters that we get to learn. So we're going to say we do this rescaling, and then we multiply by this, let's call it a weight. Okay, alpha, beta, gamma, right? And we'll add in a beta at the end. So this is going to change the mean, and this will change the standard deviation. So if we wanted a mean of 5, we could just say, we could learn that beta is 5. And if we want a standard deviation of 2, we could set this to 2.
These more hyperparameters?
These are not hyperparameters in the sense that weights are not hyperparameters, right?
Right.
So hyperparameters are things that are above all of those. So these are just more things we're learning. So we're learning for layer L minus 1 for the ith value, for the jth output, we're going to subtract the mean, divide by the standard deviation, multiply by this new value, and add this new value. Since these are learnable parameters, just like the weights and just like the biases, these are learnable too, right? The neural network is going to learn these. So the neural network all of a sudden has a very simple way that it can learn a particular standard deviation that it wants. It can just learn to change this. Similarly for the mean. Now, one thing to note here, right? This is a particular input, and we learned a beta. And now other inputs are going to have their own betas, right? So we'll have the inputs to our, right, we have our W A at L minus 1 plus B. Each of these A at L minus 1s has its own beta that it's learning. So we have W, our weight, times some value plus this B. So we're going to end up with sort of weight 1 times beta 1 plus weight 2 times beta 2 plus weight 3 times beta 3, which is, once we fixed our betas and fixed our W's, a constant. So this bias parameter kind of becomes unnecessary. So if you're doing batch normalization, we don't actually have to have this bias. All right, so what's going to happen? We've basically gone through a bunch of work in our batch normalization so that we can express everything we could express before. The difference, though, is that the standard deviation and the mean are single values that can directly be controlled, rather than just sort of the result of whatever's coming out of the previous layer. So that a given layer at layer L can more choose what it wants that will work well for its mean and standard deviation. And then the batch normalization will just rescale those things, the incoming stuff as necessary to get that desired mean and standard deviation. So since we're learning these separately, any scaling we want to do just changes the alpha or the beta. It doesn't have to change every activation down below. And this turns out to be really, really useful. Let me just make sure that I make this clear. So mu is our mean of this given mini batch. So mu is going to change from mini batch to mini batch to mini batch, but we're assuming it's some representation of the overall data. Gamma is the learned desired mean. So at the end of our training, we're going to have some calculated value, so learned value for gamma. What do we want to do if we want to do prediction? So batch normalization says we're going to go through and take a bunch of inputs, rescale them based on the mean and standard deviation of that mini batch. So we could require that when we do inference that we have a mini batch, right? That would be one possibility. So no, you can't just ask whether this is a cat or a dog. You have to give me 50 pictures, and I'll tell you all of them, but don't give me just one, right? What else could we use as our mean and standard deviation at test time? What's that? The learned mean would not be so great, and here's why. Because basically, we would And learn standard deviation, I presume too, right? So we would take our input, we would subtract out the learned mean, which is beta, right? And then we would divide by, we would use gamma here. So basically the gammas would cancel and the betas would cancel, and we would say the input is the same as the input. So the thing to keep in mind here is this is an approximation of the true mean. The mean if we took every one of our inputs. Okay? We could, I suppose, try and figure out what that is. But it's not particularly easy to do. But what we do know is as we're running our training, we're getting random samples here, right, of what our mean is. So we could just do a running average of those, right? And say, well, this mini batch we had a mean of 5, and this mini batch we had a mean of 3, and this mini batch we had a mean of 4.5, and we'll just keep that sort of running total. And that's a very easy thing for the batch normalization to do. Look at each mini batch as it comes in, calculate the mean, calculate the standard deviation, apply it here, and then also save it in this moving average. And if you save your model, save that, right? So that when we go do inference, we can use that information.
It said on the previous slide that the gamma was the learned desired mean.
Gamma is the learned desired. That is a mistake, right? Because beta is the mean, so. So beta, and then we have the relationship between sigma and gamma. Right? This is the mean of the mini batch, or if we're doing inference, this is the saved average. And this says mean, and of course this is standard deviation. And this is the learned. Desired standard deviation. Okay. All right, so we don't run inference in mini batches. We could do that, but otherwise we just calculate this moving average.
Sorry, the moving average is used as the data term?
The moving average is used as the mini batch term. So it's used for the mean and it's used for the standard deviation. Okay? Because we don't necessarily have the mini batches at inference time. And they may be different than what we use for training, right? So better to use basically the values we had for training. So batch normalization is magic is not the right word, but it has certainly made networks much, much easier to train. There is a regularization component to it. So one regularization component is since our mini batch is scaled with the mean and the variance, right? This is just approximation of our true mean and variance. And so that changes over time from mini batch to mini batch to mini batch. So there's some stochasticity there that helps with regularization. Okay? But that's not why batch normalization is used. So what we can find is, if we look, let's say, let's see. Okay, so let's look at so in ResNet, we have basically a batch normalization. A couple of different batch normalization choices here, a BN1 and a BN2, and let's just see how often. So what happens is we do our convolution, and then we do a batch normalization, and then we do a ReLU on that. So our batch normalization here is happening on our weighted input. In the original paper, that's where batch normalization was suggested to be done, is basically between the weighted input and the activation function. Sometimes you'll see it's just added as a separate layer, just directly between two other layers, and there it's obviously happening after the activation of one, before the weighted input of the other. So we do a convolution, we do a batch normalization, we do a ReLU, we do another convolution, another batch normalization. Okay. And actually, this is the actual order in which stuff is done. So do the convolution, apply the batch normalization, do the convolution, apply the batch normalization, do another convolution, apply another batch normalization, do a ReLU. Sorry. I skipped too far. When you create a module in PyTorch, you, in your initialization, sort of set up everything, and then your forward routine is where you actually make the calls. So it's in our forward routine that we are calling conv1, ReLU, batch norm1. Conv2, what's this one here? Out equals residual plus out. That's our little plus node, right? That's our skip layer, right? So we saved up above at the very beginning residual equals x, and then we added in here. So I said that the batch normalization is happening before the ReLU, and that's because I was looking at the initialization, which is not the order we actually apply the operations. So here, clearly, the batch normalization is happening after the ReLU. Questions on the batch normalization? Okay, so we are the basic idea of batch normalization is maintaining the distribution of incoming values rather than having them change all over the place. And that makes learning work better because we don't all of a sudden have to deal with this completely different distribution than we had just learned on, having that change all over the place.
So are there any
Abel.
particular scenarios where you would prefer one form of regularization over another?
So batch normalization, so dropout was invented first and batch normalization afterwards. With batch normalization, dropout isn't as necessary. There is not really a good science to this, though, and it is much more art and people trying and seeing what happens. So,
Why would dropout not be necessary with batch normalization? It seems like they're tackling different parts of the problem.
they are tackling some different parts of the problem. Without dropout, stuff just was not working well. And so dropout was a necessary requirement in order to get networks to be trained and to generalize well. With batch normalization, you can use it successfully in networks without dropout. So it's often used both together though, because you're right, they're doing different sorts of things.
Question, so before we started talking about regularization, we saw that the cost would kind of go down as you increase the number of iterations. But now that you added regularization term, do you expect that same behavior of it kind of going down? Because now we're also talking about operating on mini batches.
So this is a great question. Should the loss go down over time from one iteration to the next iteration? Actually, let's say.
How do we like kind of gauge performance over a period of time?
Yeah. We would still expect, with or without regularization, the cost to be going down. Because basically, we've just got a function that we're trying to minimize, and we're taking the gradient. And so we're hoping we get better, right? Because we're going in a descent. Why wouldn't we?
Different batches.
Okay, so that's one possibility, different batches. Because we've got a particular mini batch, right? We've trained so far on data we've seen, and now we're taking a subset of that, which is a particular mini batch. And so this mini batch might make us worse off across the entire spectrum because our gradient might not be right. It's good for this mini batch, it's not good overall. What if we trained on everything all at once? So we train on all our training examples. Is it a true gradient? If we're training on all our training examples, the gradient we got is the real gradient. It's not an approximation because we've got a mini batch. It's the gradient. It's the direction we want to go to reduce our loss. So does that mean that from one step, one back propagation step, if we figured out that gradient, that we would reduce the loss? You say no, why?
Oh, yeah, sorry. Well, I don't know if that's where we want to be, though. If we just want to take one step, doesn't mean we've gotten as close as we could.
Not as close, but is our loss better?
Yeah.
And I say no. And here's my counterexample. My counterexample is this picture with a very simple loss function, right? There's our loss function. And we're here, right? So there we are. Do we know our gradient? Yeah. Right, there's our gradient. So how can we go wrong following the gradient? We overshoot. What could cause that? The learning rate. If we had a learning rate that's too big, we could overshoot our gradient, right? So when we update, now all of a sudden, we're over, we decide, oh, if this much is good, let's just keep going down to here, right? And now all of a sudden, our new value is up here. So even if we use the entire batch, if our learning rate is too large, we still might have the loss go up from one step to the next step. And that's why we keep the learning rate small. So there's several effects going on, right? One, that our learning rate may cause us to overshoot, right? Or maybe we're very unlucky and, right, the function actually looks like, so our gradient was correct, and then it goes way up like this. Right? So we didn't even need a large learning rate to go bad. Even a small learning rate might go bad. And then the other thing that's causing us to be wrong is our gradient is not correct if we have a mini batch, because we're looking at the gradient of that mini batch. If we had a gradient of the entire batch, yes, that would be correct. All right. So gradient descent optimization algorithms. We've been using stochastic gradient descent, right? So batch gradient descent says train it all at once. Variety of problems with that, right? A giant problem is that the entire batch doesn't fit in memory, right? In GPU memory. So we don't get all our fancy vectorized computations. What's the second reason? That batch is going to be slower than mini batch approach. Let's say
What if we don't have all the data?
well, if we don't have all the data to begin with, that's another problem. And that's where we get into like online gradient descent, where we're just going to take the input as it comes, one at a time, because we're just getting some, let's say, stream of data. So that's a case. So let's say we have 10,000 input values. And I'm saying, wait until we have calculated the gradient for all 10,000 of them before we update the weights. In the mini batch approach, if we had a mini batch of 100, we would say, take 100 of them, find out the gradient, update the weights. Take another 100, find out the gradient, update the weights. So we are adjusting our weights to be better as we go, as opposed to waiting 10,000 steps, right? Waiting to look at all 10,000 inputs to get the true gradient. Yes, we've got the true gradient, but we could have been adjusting these weights, not 100% correct, but more, so that by the time we get to here, we're better. So stochastic gradient descent. When you see the term stochastic gradient descent, sort of one extreme into this is they mean one training example at a time. Okay? And there, our gradient jumps around quite a bit, right? And our loss is going to jump around quite a bit too, because this particular instance may take us in a gradient that's in the entire opposite direction from what all the rest of the training examples want. But in general, stochastic gradient descent really these days means mini batches. But just be careful, sometimes when it's used, it just means one at a time. Okay? We don't like one at a time, both because it jumps around a lot, but mainly we don't like one at a time. Why?
Slow.
Yeah, it's slow. Because basically, we can do 100 at a time at the same speed we can do one at a time if we run on a GPU. Assuming we've got the memory that it can all fit. So. Okay, we need this learning rate because we need to know how far to go along the gradient. We know we're updating the parameters independently. We know about learning rate schedule. We saw an example right before where we have a learning rate schedule. And often it's a fixed learning rate schedule, but you could also have some variable rate learning schedule that is somehow looking at the loss or how the loss is changing and affecting the learning rate. All right, so let's look at our stochastic gradient descent. Theta, what does theta represent here? Our parameters. Right, where our parameters are all the things we can learn. Right, so give me an example of things this might be. Weights, biases, two new ones. Say that again? Yeah, so the batch norm values, batch norm variables. So our theta is being updated every step by multiplying the learning rate. I figured let's not just use yet another Greek variable here. So our learning rate times the derivative j with respect to theta of, so as I'm showing here, j is a function of our parameters, but also j needs to know our input and our targets, right? Because when we're calculating loss, a lot of times we want to know how good did we do compared to ground truth, which is our targets. And we want to know how do we do on these particular inputs. So we need that as part of J. So that's stochastic gradient descent. If we have stochastic gradient descent sort of in the extreme case where we just have one input, then we just basically have a batch size of 1. All right, so let's say we've got a bowl shape, okay, an elliptical bowl that is our loss function. Okay, so it's in one direction, it's wide, and if we look at it in the other cross section, it's narrow. And this shows kind of a contour map of that, right? So every value here, every line represents a height, right? So this is, height 3, height 2, height 1, and so on. And we're trying to get low in here. So if we look at this as the a-axis, and this as the b-axis, and we are at a particular point on this three-dimensional map. So let's say we're here. In which axis is it steeper, our gradient? We're steeper here, right? Because this is less distance to go from, let's say 3 to 2 to 1, than in this distance where we go from 3 to 2 to 1. Okay, so we're steeper here than we are here. So therefore, when we are doing our gradient, it is mostly down. Would you agree? And we've got some amount of b-axis, but it's mostly x-axis. So we are going to be traveling, I'm going to just make it a little farther here. We're going to kind of be traveling like this to get to the center, where we keep going back and forth on our gradient on the b-axis, on the a-axis. On the b-axis, we're going to just always continually go to the right. But on the b-axis, we're going to go up and down, up and down, up and down, and up and down, and up and down. Does that make sense? Okay. This is slow. We're exactly opposite of what we want. What we really want is in the a-axis, we don't want to move very much. And in the b-axis, we'd like to move a lot. And that would get us here quicker. Okay? So that's our goal, and we're going to look at how we can accomplish that. If we dropped a marble here, what would the marble do? Would it follow this path? Why not? Its horizontal speed would continuously increase until it reached terminal velocity, right? So because we're repeatedly applying the force to it, right? And so therefore its velocity is increasing, increasing, increasing until friction or air resistance causes us to hit terminal velocity. That's what we're going to do. So the fact that it has momentum is what makes this work. So we are going to add momentum. So here's the idea. We're going to use history. If we've got a gradient that is small but consistently in the same direction, just like our B example there, make larger changes. Conversely, if we've got a gradient that's large but that keeps changing direction, don't go so much. So here's what we're going to do. We're not going to change the position of the weights based on the gradient. We're going to change the velocity. Okay? So that we are going to have a history of that velocity. And so if we have slow but steady changes, that velocity is just like the ball is going to be increasing, increasing, increasing. Where if we go in one direction and back the other direction, back the other direction, we're going to be adding those vectors, and so our overall movement is not going to be much. Does the concept make sense? So here's what we're going to do. We're going to say that the velocity is a fraction of its previous velocity. We're not going to entirely use the previous velocity, so we're going to have some exponential decay. Minus, so this is not an uncommon way when we're parameterizing two values to use, let's say, beta and 1 minus beta. So we could just adjust the fraction that we're getting from one versus the other. You could get rid of the 1 minus beta, but it's a useful sort of paradigm to see. Because the gradient's in the same reason that we subtract from the weights, because the gradient's in the other direction. Yeah. So we calculate the partial derivative, we multiply by the learning rate, and then we say, okay, we're going to take some portion of that plus some portion of our previous velocity and make that our new velocity. And you can see how this is going to be creating a velocity, right? And there's going to be some maximum velocity, right? The terminal velocity, I believe we've just calculated, is going to be that, except I find it very unlikely there's going to be an alpha here. So, yeah. And then update the weights based on the current velocity. Okay, so this is stochastic gradient descent with momentum. Works well. Okay? You could have a momentum schedule. So you may say, for instance, we're going to have a smaller momentum to begin with. Okay? And then increase that over time. So that's momentum. There's a slight tweak to the momentum. First, any questions about the momentum? Okay, there's a slight tweak, and here's how the tweak goes. Let's say you've got so we're trying to minimize that. And we are here. Okay? And we know then our gradient is here. And yeah, okay, so let's say this is our gradient, and then we also, in a different color, have the accumulated velocity. So let's say our velocity happens to be, I don't know, like that. Okay? So what our momentum says is we take our current velocity. I'm going to ignore the betas for a second. And then we add in our new gradient. And this will tell us, with our vector addition, where we want to go this time, right? So we're going to go, green was not a good choice. So that says we're going to go here. Do you agree? So we have our, old velocity, new gradient, new velocity, and then we're going to update our weights based on that new velocity. So that's going to take us from this red position down to here. Okay, assuming this is the same vector as that. Here's the problem. We used our gradient where we are, and we said, we want to go in this direction. And then we add it to the velocity, which is also going to take us in the whatever the velocity direction is. And the combination of those might not be great. What might be better instead is say, don't calculate the gradient where you are. You know you're going to be moving by the velocity. Move by the velocity and calculate your gradient there and add that gradient. So add an after gradient rather than a before gradient. So here we calculate the gradient first. And then we add to the velocity. And the Nesterov momentum says calculate the gradient after you move by the current velocity. And then update. The velocity. And move by the gradient. So first we move by the current velocity, we calculate the gradient, we update the velocity, and we update our position again, right? So we do 2 moves separately. So this 2-step basically says we will have a better understanding of what the gradient is after we move the amount we already know we're going to be moving anyway, which is the velocity, right? The old velocity. Does the concept make sense? So it just does a little better because it avoids these situations where the velocity is taking you past where you want to go. But since you calculated the gradient before you looked, you're going even farther.
Question.
Uh-huh.
So the first move in the S-drop momentum is like it's a pseudo move, like we're not actually moving like the to there, but like we're just calculating what would be there, and then we're still moving from the original position. It's unclear on what real means. So I can imagine different implementations, right? I can imagine one implementation that says, go update the weights based on the current velocities, and now backpropagate, okay? Which will give you your gradients, and then go apply the gradients and update. And that way sounds less like a pretend to do it and more like do it, right? Go ahead and update the weights and then calculate the backpropagation. And so you would be updating the weights twice in that case. There's probably a way to do it as well that's as if, where you calculate the gradient as if you changed it, but you really haven't changed it. But just in my quick thoughts about it, that seems like it'd be hard. It'd be easier to just do it. Go ahead again.
So it seems like from the formula, at least, if you were to act like genuinely move by v of t minus 1,
Uh-huh.
compute the gradient, and then move by the gradient, it seems like your net move would be vt minus 1 minus gradient. Whereas what it looks like you're actually doing is moving beta vt minus 1 minus like 1 minus, like you're moving like.
Actually, given you have the bait, well,
It seems like you are doing like what if I was over there and now adjust my velocity accordingly, and then it's at least that's how I'm.
yeah. So let's look at this. The Nesterov momentum says instead of calculating this at theta, calculate at theta plus the old velocity. That is the difference.
And
Right.
then you actually, and then the theta is adjusted by vt in the second step.
Shouldn't that be the gradient also like this?
So conceptually, this is what is happening. How we're practically doing it, right? Are we actually applying this vt minus 1 addition to this theta,
Right.
and then calculating this? In which case, we don't want to add vt. We want to add vt minus 1, right? We want to just add the delta. So either way could work. But that is the basic difference. And this is similar to the vector diagram I was showing. This is actually from the paper. So this shows that we're calculating the gradient at time t. We have our old velocity, and so we're going to just move by the sum of those vectors. And here we are conceptually basically applying our velocity and then calculating our g and going, yeah.
What is the mu vt?
The mu vt is their beta. I'm sorry, it's the paper actually used. Different Greek symbols. Okay. The last thing we're going to talk about, which we'll talk about on Wednesday, is per parameter learning rate. That is, what if we could say, for this weight, we'd like this learning rate, and for this weight, we'd like this other learning rate, and adjust the learning rates on a per parameter basis. That'd be even better, and that's what we're going to see then. As far as the midterm, I think I've decided, given that
you guys have the break. What's the name of the break? Fall break. That's a good name. And also, given that the drop time is the week after that we're going to have an in-person, in-class midterm next Wednesday. Okay. I mean, I could give it out and have it due on Thursday if that would be better, but I was thinking that would make sense. Any thoughts right now?
So it's next Wednesday?
It's a week from Wednesday. Yes. Okay. And as far as your next assignment, it will be a programming assignment again. And since you have a midterm next Wednesday, I'm assuming you would prefer not to have this due Tuesday night of next week? Yeah. So it'll be due the following Tuesday, but I'm going to still try and hand it out Wednesday. If I can't hand it out Wednesday, I'll hand it out next Monday.
Up until which lecture will the stuff be covered for the midterm?
So the midterm will certainly cover through Wednesday, this coming Wednesday, and I'll say not Mondays. So there will not be a sample midterm. Sorry. I would imagine that there will be multiple choice questions and some calculations you'll need to do. You will not need to like run an entire back propagation like you had to do, where you'd really want to write a program for it. That won't be necessary. That being said, you'll need to know how to do the back propagation, right? I may give you a particular piece to do. I am asking you general questions about it. And a lot of it is going to be just conceptual understanding. So one question that I thought would be really good, but that I gave away, would be, what if you had gradient descent across an entire batch? Are you guaranteed the loss is going to go down? Right, from before backpropagation to after backpropagation. We know the answer is no, and our counterexample is large learning rate, let's say. Yeah.
Are we allowed to have a cheat sheet outside it?
So yes, you may have one 8.5 by 11 handwritten piece of paper. One, I didn't say that, you're right. One single-sided 8.5 by 11 piece of paper. And you'll just turn that in with your exam.